This video, we're going to go through a fairly important topic. It's called a function defined by an integral, or you could also call it an accumulation function. Why? Because we're going to accumulate the area, right? That's what the accumulation function is, what these functions defined by integrals do. They're going to be defined by an integral. It's going to start at a point, and then we're going to accumulate the area bounded by some graph, starting from my point, going to whatever other x value it wants. But yeah, they're going to a lot of it's not going to be new, okay? A lot of this stuff is going to tie back to stuff we did first semester called the derivative connections. Remember, if we're given the graph of the derivative, there's all sorts of stuff we can answer about the original function. In fact, let's just recap that really quickly before we get into the new stuff, because the new stuff is only going to add like a little bit, and then we have all that old stuff from the past. Let's recap the fun chart. Let's make sure I'm on the screen. Okay, there we go. So we have this fun chart. Remember, the first derivative, that's the same thing as the slope of f. This first derivative is the slope of the layer above it. The second derivative also is the slope of the layer above it. So f double prime, that's the same thing as saying the slope of f prime. Here we go. If the first derivative is positive, that means the slope of f is positive. That means f is going up. F is increasing. Okay. If the first derivative is negative, that means the slope of f is negative. That means f is going down. That means decreasing. The sign of the first derivative will tell us the behavior of the original function. If your first derivative is positive, that means increasing. If your first derivative is negative, that means the layer above it, the original function f, is decreasing. First derivative tells us the slope, tells us the behavior. Slope and behavior, synonyms. Now the second derivative being positive. The second derivative, positive, means the slope of f prime is positive, which means f prime is increasing. And if f prime is increasing, that means the slope of f is increasing. That means the slope of f is getting bigger. And if the slope of f is getting bigger, that means it's going to have an upwards curvature, which we call concave up. Okay, so the second derivative positive happens when the first derivative is increasing. It also happens when f is concave up. All three of those happen simultaneously. The intervals where f is concave up are the same intervals where f prime is increasing, which is the same intervals where the second derivative is positive. All three happen at the same time. Okay, last part of the fun chart. If your second derivative is negative, that means the slope of f prime is negative, which means f prime is decreasing. And if f prime is decreasing, that means the slope of f is getting smaller, right? Decreasing means getting smaller. If the slopes are getting bigger, it means concave up, bending upwards. The slopes getting smaller means the graph is going to be bending downwards. It's going to be concave down. So the first derivative and its sign tells us the behavior, increasing or decreasing. What's my function doing? Is it going up or is it going down? That's what the first derivative answers. Second derivative and its sign, positive or negative, that tells me the shape, or it tells me the curvature. It tells me the bend. It tells me how it's increasing or how it's decreasing, right? It tells me the concavity. Is it increasing at an increasing rate, or is it increasing at a decreasing rate, right? That's what the second derivative will tell us. The curvature or the bend or the shape of that original function. And then we also had this little transitional diagram. Like, what does the graph of f prime correspondingly tell us about f? Okay, so let's recap this. It's the same conceptual thing as the fun chart. It's just written in a slightly different format. There was 4 things that translated all very directly. We'll do this as a recap, and then we'll get into the new stuff for today. Remember, this is not new, right? This should all be stuff that you should know well because we did it a lot first semester. But in case you forgot, we'll review these really quick for you. First thing is the sign or the location of your first derivative. Remember, this is if you're looking at the graph of your first derivative and you're trying to answer questions about that original function f. Okay, the sign, whether it being positive or negative, or the location, I mean above or below, right? So those, you can think about it either way, whether it's positive or negative, above or below. Positive is above, negative is below. So you can think about it as the sign or the location, but that's going to end up telling me, right, the sign of the first derivative, that tells me the slope of the original function. It tells me the behavior. So the sign or the location, that's going to end up telling me the behavior of your original function, whether it's increasing or whether it's decreasing. Or constant, right? If the sign is 0 or if the location is on the x-axis, then it would be constant. Okay, so where it is, positive, negative, or above, below, that tells me the behavior, increasing or decreasing. The next thing would be the x-intercepts. Right, the x-intercepts of your derivative, those are the places where the sign changes, or those are the places where the location changes. So correspondingly, that means that's going to be where f changes behavior. And if f changes from increasing to decreasing, that's a max, or if it changes from decreasing to increasing, that's a min. Right, the x-intercepts are where f prime changes sign or changes location. That means the x-intercepts for the derivative. That's going to be where f changes behavior. We call those points extrema. Now, how it's an x-intercept matters. If it's an x-intercept but it does not cross, then it's neither a max nor a min. If it's an x-intercept but it crosses from above to below, positive to negative, then you would have a relative maximum for f at that point. Or if it's an x-intercept where it crosses from below to above, from negative to positive, then your graph would change from decreasing to increasing, and we know that location would be a relative minimum for f. But in general, if you want to know about the extrema for your original function, you would look at the x-intercepts, and specifically how it's an x-intercept means makes a big difference. Okay, next we could look at the slope, or we could look at the behavior of that first derivative. Slope and behavior, those are interchangeable words, right? So here I'm looking at, is f prime increasing or is f prime decreasing? If the first derivative is increasing, right? If the first derivative has a positive slope, that means your second derivative is positive, right? If f prime is increasing, that means f prime has a positive slope. That means your second derivative is positive. That means f is concave up. Or if your slope of f prime is negative, if f prime has a negative slope, that means f prime is going down. That means f prime is decreasing. If f prime is decreasing, if f prime has a negative slope, that means the second derivative is negative, which will in turn lead you to concave down for f. So the slope, aka the behavior of your f prime function, the slope of the derivative, tells me the concavity of the original function, where it's concave up, where it's concave down, and then last but not least, where the derivative changes slope, right? So that's going to happen at your extrema, your maximums and minimums. That's where your slope changes, or that's where your behavior changes. The extrema, the max and mins of the derivative, right? The extrema is where the slope changes. That means correspondingly, it's going to be where the concavity changes. We call those points of inflection, right? So anything you wanted to know about your original function, you could pretty much tell by looking at a specific characteristic of the first derivative. We've done all that stuff before. It's called derivative connections. The fun chart and this little transitional diagram, they're really the same thing, right? They're just different ways of visually representing these concepts and these connections, these relationships between the three layers. Here, I think this is nice. If you're looking at the graph of f prime, it makes it very easy. What is it going to tell me about f? Here is just a little bit more abstract via the fun chart. But this stuff is what we're going to be doing today. We're just adding on a little bit more now that we know integrating, right? Integrating the derivative. When I find the area bounded by that derivative, right? So I guess we could add this on, right? The area bounded by the derivative. We know that fundamental theorem of calculus. The area bounded by the derivative, that's f of b minus f of a. That's your change in your y values for your original function. So that area bounded by the derivative, that's going to be the change in the y values for your original function. How much it goes up, or how much that y value goes down, that's based on how much area you accumulate. If you accumulate positive area, your graph's going to go up. How much does it go up? It depends on how much area you build in. Or if you're changing your y values, your graph could go down. That would happen if your derivative accumulates negative area. So I guess this is the new stuff for today. The area bounded by the derivative, right? We could say x from a to b. That's going to be your change in your y values from A to B, right? That's what my fundamental theorem of calculus is, right? This is what your fundamental theorem of calculus tells you. The area bounded by the derivative is the change in the y values for your original function. Right, so we're just doing more of this derivative connection stuff today. Now there's a little bit of a wrinkle because it's a function defined by an integral. Instead of this thing explicitly being labeled f prime and then being asked about f, it's a little bit sideways. So let's go through, let's do this page. We'll probably end this video after this page, and then the second video in this playlist will cover the rest of the packet. Okay, so here we go. Functions defined by integrals, aka accumulation functions. Always pay attention to what your pivot point is, right? I always like to kind of put a little bit of a dotted line. X equals 0, that's my pivot point. That's where I'm either going to start to accumulate area or potentially to lose area. Let's go for it, right? We have g, which is the integration from 0 to x, and I'm going to integrate the f function. Okay, so g is an accumulation function, or g is this function defined by an integral. Let's go ahead and do it. Part A is the new stuff. It says g of 0. Let's see, I need to make sure I stay on the screen, so let me try to do that for us. So we go, g of 0. Now I have the equation for g, so if it wants g of x, you just plug in the x value, right? So g of 5, I would plug in 5. If I want g of 0, I'm just going to plug in 0. So g of 0, that would be the integration from 0 to 0 of the f function. I'm not going to write f of t dt because I need space, but it's just going to be 0 to 0, right? It starts with 0, and then you plug in whatever that x value is. So g of 0 is the integration of f from 0 to 0. And I know if those two numbers match, the answer is going to be 0. So there we have it. G of 0 is 0. Got that one done. Like, pretty easy. Now let's do g of negative 1. G of negative 1 would be the integration from 0 to negative 1 of the f function, which means I'd want the area bounded by f from 0 to 1. So it starts at 0, and then it works its way backwards to negative 1, right? Here's negative 1. Now, when I'm integrating right to left, everything's kind of backwards, right? The region above the x-axis will count as negative, and if you had regions below the x-axis, like something down here, it would count as positive. Whenever you're working way backwards from the pivot point, everything is reversed. Stuff above counts as negative. What you could also do, if you don't want to remember that, right, you could flip it, right? Instead of doing 0 to negative 1, you could do negative 1 to 0, but if I flip the order for the integration, remember all I'd have to do is stick this little negative sign in there. So if you don't want to think about going right to left, if you don't want to go from 0 to negative 1, if you don't want to go backwards, because you don't want to remember, hey, if everything's backwards, everything's reversed, right? Positive is negative. The above is negative. Below would be positive. You can just always flip it, right? Here I'm going from negative 1 to 0. That's left to right. So here it's going to be positive. So now this is going to be positive, but I will just subtract the positive number. This will have the negative built in. This one has the negative out in front, right? So this is a negative number. This is a positive number. But when you have the negative of the positive number, those two things are the same, right? I would probably recommend that you flip it. Then you just work from left to right. We like working from left to right. So just flip the integration and put the negative in. Here we go. That area, we can do it using geometry, right? You don't need to do calculus. It's a geometric triangle, so you can just use geometry. 1/2. The base of that triangle is 1. The height of that triangle, you can count it as 2. So I know the area of this region is going to be 1. But since I was working my way backwards, this end result will be negative 1. Okay, cool. Let's look at the next one. So we got that one done. Let's do g of 2. G of 2 would be the integration from 0 to 2 of f. That's easy. 0 to 2. That would just give us, let's do it in red. It'll give us this little red region. So 0 to 2. And since it's already left to right, it's all going to be positive. So that's a quarter circle. So it's going to be 1/4 pi r squared. The full circle is pi r squared. Since that's only a quarter circle, you divide it by 4. Okay, so 1/4 pi r squared. The radius of this sucker is 2. Ooh, look at that. 2 squared is 4. So that's going to cancel. This answer will be pi. That one's done. And then the last one, g of 5. Plug it in would be the integration from 0 to 5. Okay, so I would need all of this area, starting with 0 all the way to 5. Let's see, so 1, 2, 3, 4, 5. Don't assume that that's 5, right? Always count it. Sometimes they're mean and they'll stop it early. This is 5. So when I do this integration from 0 to 5, I'm going to have this area, which I already know that area, right? All of this area was pi. You don't have to recalculate it. We know it. And then I'm also going to accumulate in this next region, and that region is going to be negative since it's below the x-axis. Moving from left to right, above is positive, below is negative. If you're ever working backwards, right to left, above would be negative, below would be positive. Everything's backwards when you're working backwards. Okay, but here when we're doing left to right, that counts as positive. We already know how big it is. This is going to count as negative. Let's go get the size of this region. Let's see. You can break it down a couple different ways. I'm going to break it down like this, where we have a triangle right here, and then we could do the trapezoid right here. Okay, that's fine. If you want to do a triangle, rectangle, that's okay. Or if you can see, hey, like this and this, they would combine and they would give you like kind of 2 units worth of area. But somehow, just using geometry, you would need to know that the area of that region is 4. Since it's beneath the x-axis, it's going to accumulate as a negative 4. So here would be that y-coordinate of g of 5. Right, it'd be pi minus 4. You start with 0. Remember our pivot point, that tells us where we're starting with 0. When I accumulate in that positive area, it's going to cause my y value to go up. How much does it go up, right? From 0 to pi, how much does it go up? It depends on how much area you encapsulate. Since that's pi units worth of area, your y-coordinate goes up pi units. And then here I'm going to encapsulate 4 units worth of negative area, so then this y-coordinate goes down 4 units. Okay, so this accumulation function, or this function defined by integrals, kind of ties back to some stuff we've done in the past. The area that's positive makes your y values go up. The area that's negative makes your y values go down. Just be careful when you're working from the pivot point backwards. Everything's a little bit reversed. But there we go. That's part A. Using this derivative, we could find these other y coordinates based on that accumulation function, or that function defined by integral. Let's look at part B. It says where or on what intervals is the graph of g increasing? Where is it decreasing? And of course, we're going to justify our answers, right? We're always going to justify our answers, always, right? No excuses, always. Even if it doesn't tell you, always justify, right? There's no point not to. Now, I know g would be increasing. G would be increasing. I guess we'll just write it right here. Okay, so g would be increasing when g prime is positive. That's what it means for something. I'm kind of getting sideways here. Let me fix it. G would be increasing when g prime is positive. We know that. And g would be decreasing when g prime is negative. We know that, right? That's the very basic definition of increasing and decreasing, right? The fun chart. The fact that this is f prime and f doesn't matter, right? This is true for any function, regardless of what letter it's using. If I want something to be increasing, that thing's derivative must be positive. Or if I want something to be decreasing, that thing's first derivative had better be negative. So I somehow have to figure out how I can determine the sign of that g prime. I'm given g, and I have the graph of f. Let's see if we can connect them. Okay, now everything is kind of based on this. Come on, blue pin, you can do it. Oh my, you're almost done. Come on, there's like 20 minutes left. You're good. Here we go. We've got this this relationship. G is the integration of f, right? That's kind of the whole key to this entire question. G is the integration of f. So if I want g prime, if I take a derivative on the left, that means I would also have to take a derivative on the right. And we just did the second FTC. We know when I take the derivative of that integral, they're going to cancel. So if g is the integral of f, that means if I take a derivative, g prime is f. Okay, so this graph was labeled as f, but really it's just g prime, right? And we know if I'm given the graph of the derivative, I can pretty much answer anything we want about the original function, right? The same thing is going to hold true. It's just instead of it being labeled as g prime at the onset, it's labeled as f, but then you're kind of told g prime is f, not directly, but it tells you g is the integration of f, which means g prime is f. Let's do one more really quickly. G double prime would be f prime, right, which is the slope of f. There we have it, right? So this graph is g prime. It wasn't initially labeled as it, but it is. Okay, now let's go through, answer all these questions just like we could have done in the first semester. Here we go. G is increasing when g prime is f, is greater than 0. That means where is this graph positive, which happens in this interval and in this interval, right? Where the derivative is above the x-axis, that's where your original function is increasing. So that will be from -1 to 2. You don't need to split it up, right? You don't need to do -1 to 0, 0 to 2, right? That whole thing is positive up above -1 to 2. And then g would be decreasing when g prime is f, when that graph is negative. So when this graph is below the x-axis, which happens from 2 all the way to 5. So 2 to 5. You could put a bracket on the 5, but really, let's see, it doesn't really kind of tell us not to. So if you wanted to, you could put a bracket. If you were to put a parentheses, I guess it's really never going to cause you to get the answer wrong. You're not going to dock a point because of putting a bracket instead of a parentheses, right? It's okay. But the key to this whole thing was this function defined by the integral and knowing, hey, if g is the integration of f, that means g prime is f, right? If you have this written somewhere on your page, you will usually get one of the 9 points on a free response question, right? This could be a free response on an AP exam, and just purely having this, even if you don't even answer anything, just having this would get you 1 point, right? So please make sure you write it. By the way, if you have this written somewhere on the page, you don't have to keep writing it. I'm going to keep writing it to try to give you guys the extra reinforcement, but if you have it written somewhere, like here, that would be a really good place to write it. You don't have to keep writing the same thing. You could just say g prime is increasing when g prime is greater than 0, or you could say where f is greater than 0. Right? You could do either. You don't have to keep writing this part if it's defined somewhere else on the page for you. Yeah, there we have it. Above, positive, that's increasing. Below, negative, that's decreasing. We know that, right? We've done it before. Part C says find all the values on this open interval where g has a relative extrema and classify each as either a max or min. Right? We know how to do this, right? We look at the x-intercepts of that derivative to determine the relative extrema for your original function. So here we go. G has relative max when g changes from increasing to decreasing, which means g prime, which is f. Sorry. Okay, let's recap. I know, sorry, I was way off the screen. I didn't even realize it till it's too late. G has a relative max when g, that original function, changes from increasing to decreasing. That's what it means to have a max, right? A highest point. It was going up, then it changes, goes down, right? When g changes, increasing to decreasing. That means when g prime, which is f, g prime, which is f, changes from positive to negative. So I'm going to go look at this graph and determine where it changes from positive above to negative below. So therefore, at x equals, let's see, where on this graph, where do I have the x-intercept where it crosses from positive to negative? It happens right here, right? That's your only x-intercept where it crosses. You have another x-intercept over here, but you don't know that it continues on that same pattern. You don't know. So right here at x equals 2, we know we are going to have a relative maximum. Now, you could also just look at this, right? You've already done the intervals of increasing and decreasing. So you could just look, where does it change from increasing to decreasing? Well, -1 to 2. Oh, look, at 2 is where it changed, right? So you could do that, and that would be fine. But you could also write either of those two justifications. Now, let's look at the minimums. G has a relative, am I on the screen? Yes, I am. That's lucky. Here we go. G has a relative minimum when G changes from decreasing to increasing. Therefore, g prime, which is f, changes from negative to positive. We know it's the x-intercepts of the derivative that end up being extrema. The x-intercepts that cross from above to below, those are relative maximums. The x-intercepts that cross from below to above, from negative to positive, those would be the minimums. The issue is that this just doesn't have any. right? This particular derivative, it wasn't originally labeled as the derivative, but it kind of sort of was. This derivative doesn't ever cross from below to above. If this extended, then you would have a minimum at -1, but since we don't know what happens to the left of it, we can't conclude it. We only had the one x-intercept where it crossed, and since that one crossed above below, that one's a max. We don't know about that one. If it would have continued, it would have been a min. That one doesn't even get back up to the x-axis, so for sure that one's not anything. Here we're not going to have any relative minimums. Okay, and remember, right, instead of, let me get a highlighter, instead of writing all of this stuff and all of this stuff, you could just say, hey, G has a relative max at x equals 2. And then you could say, hey, G has no minimums. You could just kind of write the answers. And then instead of doing all of this stuff, which is highlighted, remember, instead of all of this, you could say 4 words. By first, I don't know why I put a dot after the first, by first derivative test. The first derivative test tells you all of this stuff. Now, if you tell me all this stuff, you don't have to cite the test. Right? You could write either of those. That's a perfectly good justification. You could write either of those. That would be a perfectly good justification. Or if you don't want to write any of that, you could say, I probably shouldn't put that finger there. You could say, hey, here's the answers. There's the max. There's no mins. You could say all of that. And by first derivative test would justify both the maximums and the mins, or the lack thereof, would justify both all in one fell swoop. So by first derivative test, that's what you could say instead of all that stuff that's highlighted. Right? All right, part D. Sorry, I'm losing my concentration trying to get this thing level. All right, here we go. Find the absolute minimum of G on the interval -1 to 5. So do candidates test and find the x value at which this occurs. Okay, great. Candidates test. We're going to do the minimum and the maximum. Why not? We're going to do both. Who cares? Why not? We're going to do everything. Question could have easily changed one word and it would be different for us. Candidates test. We're going to make a little table. Let's see, is this going to be on the screen? Going to make the little table. Oh, it's G, right? It's G, sorry. G of x. So we're trying to find the absolute max and the absolute minimum for G. So we need to figure out what are the y coordinates of G. Now I know I always have to put my endpoints. That's lovely. And then if I have any critical points in between, I would want to plug them in as well. I did have the critical point at 2. And then here for these functions defined by integrals, we should also test the pivot point. Sometimes, most of the times, the pivot point won't be important. But occasionally, like every blue moon or so, just because of how easy the function is, like it could be just decreasing on both sides. It's rare. But I would rather be safe than be sorry. I would just always put the pivot point, right? So you got the endpoints, you have the critical point, you have the pivot point. And luckily, we already knew all of those y values. Remember back in part A? It's like, oh, G of 0. Oh, G of -1. Luckily, the question, right? It's almost like someone had planned it, right? Almost, thank you, teacher, for planning it. Right? All the work that we needed, we already did it in part A. I'm just going to copy the values. Here we go. Just copying these from part A, right? G of -1 was -1. G of 0 was 0. G of 2 isn't 2. G of 2 was pi, and then G of 5 was pi minus 4. Okay, so let's think about these values. Remember, this would be about 3.14. That's 3.14, more or less, minus 4. So that's going to be about -0.86, right? Just so we can kind of get an eyeball test and get a feel for how big these numbers are. Candidates test. Just list all the candidates, which means my endpoints, and then all the critical points and the pivot point in the middle. We're going to find the y values for them, and then we're going to figure out, okay, look, that one's the biggest one. Okay, so here we go. G has, okay, I'm tired of this pen. Sorry, I'm going to audible. Switch it to the other blue pen. G has an absolute max value of pi when x equals 2 and absolute minimum value of, let's see, the smallest value. That one's negative, but that one's more negative, of -1 when x equals -1, right? You kind of set it up as this sentence stem. You have an absolute max value of blah when x equals blah, right? You find the biggest number, that's where it hits it. And then you also say absolute min value of yay when x equals blah, blah. Right? You find the smallest value and the value where he hits it. And if sometimes the question will only ask, like, what's the value? Or sometimes it'll ask, where do you have the max, or where do you have the min? So sometimes it'll only ask for the x, sometimes it'll only ask for the y. This asks for both, right? It asks for the value and the x value. Now, it only did min. We did the maxes also, just for funsies. But I always encourage students to put both, right? If you write this little sentence stem, if you always give both, then you can't possibly be taken off, right? If you give them the x and the y, well, if they ask for the x, great, it's there. If they ask for the y, it's there. If they ask for both, it's there, right? If you always give both, you're covered. So that's great. Even though this question didn't do the max, I just wanted to show the work for you anyways. All right, cool. Let's move on to parts E and F, then we'll be donesies with this page. Good riddance. All right, here we go. Part E. On what intervals is the graph of G concave up? And then where is it concave down? And of course, we're going to justify our answers, right? We always justify our answers, right? The table is the justification work, right? The table is not the answer. The table is the justification. This is the answer. Table is the justification. Here we go. We're going to do concavity. We know if I want concavity, the second derivative would be positive, or the first derivative could be increasing or decreasing, right? We know concave up is when the second derivative is positive, first derivative is increasing, or concave down, vice versa. So here we go. We're going to write this stuff. We also know if I want the concavity for that original function, I'd be looking for the slope or the behavior of that first derivative's graph. Okay, so here we go. If I want G to be concave up, that would happen when G double prime is positive. Now, G double prime is f prime, right? The slope of f. So G double prime is f prime. Again, you don't have to write this if it's already up above on your page somewhere else. That means G prime, which is f, right? If we're thinking about the second derivative being positive, that means my first derivative has a positive slope. So is increasing. If you want concave up, the second derivative is positive, or the first derivative is increasing. It's really kind of confusing, right? First derivative, second derivative, make sure you label G double prime, G prime, GF, F prime. Always make sure you label everything. I know it's a little bit confusing though. Second derivative of G, which is the first derivative of F, that has to be positive. But this is the graph we're actually looking at. We're looking at G prime. It was labeled as F, but we're looking at G prime. So we need to figure out, where does this graph have a positive slope? Because where this graph has a positive slope, that means the second derivative of G is positive, which means G is concave up. And this graph has a positive slope in this interval from -1 to 0, and then also in this interval from 3 to 5. So -1 to 0, because this little piece is increasing, and then also 3 to 5. Okay, let's see. Am I back on the screen? More or less. Therefore, -1 to 0 and 3 to 5. And then we would just have the corresponding statement for the concave down. G would be concave down when G double prime is negative. G double prime is G prime, or sorry, is F prime, right? G double prime is F prime. That's great, but I don't have the graph of G double prime. I have the graph of G prime. So see, if the second derivative is negative, that means your first derivative has a negative slope. That means your first derivative is decreasing. So I'd want G prime, which is F, to be decreasing. So let's go find the intervals where G prime, which is F, is decreasing. Here for sure, right, the graph is going down. Here for sure, the graph is going down. Technically, at this point, there is no slope because it's got a sharp turn. So the best answer, I think, would be to say 0 to 2 and 2 to 3. If you were to just say 0 to 3, though, no one's going to throw the Bible at you. If you'd put 0 to 2, 2 to 3, you'd be okay. If you'd put 0 to 3, you'd be okay. I think the better answer would be this, right? This is not true at x equals 2, which means this is not true at x equals 2, which means this is not true. I said this, it's off the screen, right? Since there's a sharp turn at 2, that means it's not a negative slope. There's no slope at the sharp turn. And if this isn't true, that means this isn't true, which means this isn't true. So I think the better answer is to throw it out. But if you were to lump them together and say 0 to 3, like, that's okay. But I think that's the better answer, right? The AP exam will probably lump it together. Okay, cool. That's just how they define increasing or decreasing. I think it makes more sense the way I do it. Whatever. Okay, last one. Find the x-coordinates of each point of inflection on the graph of G, of course, in my interval. And of course, we're going to justify. Why would we not justify the answers? We're always going to. Okay, here we go. G has point of inflection when, bunch of justifications you could say, but the basic one is G changes concavity. Right? That's the definition of a point of inflection. Something has a point of inflection when that very same thing changes concavity. And look, we just did the concavity, so you can just take a look-see at where it changes. At 0, it changes, and then at 2, it didn't change. So at 0, it changed, and then at 3, it changed back. So I know, therefore, at x equals 0 and at x equals 3. I know those are going to be the answers. What other justifications could we have put? Well, let's look at the fun chart. If I want a function to have a point of inflection, that means it's going to change concavity. That means the second derivative is going to change sign. So I could say, therefore, G double prime, which is f prime, changes sign. That's great, but we don't have the graph of G double prime to look at. We have the graph of G prime. So we could say, hey, if we want something to change concavity, that means the second derivative changes sign. That means the first derivative changes slope, or it changes behavior. So you could say also G prime, which is f, changes slope. Or if you don't like the word slope, you could say behavior. Behavior is the better, more mathematically precise word. You could also say where G prime, which is f, has a relative extrema. Remember, the places where this derivative changes extrema or changes behavior, right? If your graph changes behavior, that means it's going to have an extrema. So wherever we have maximums and minimums on the first derivative, those are going to be the points of inflection. Points of inflection are where the slope is the steepest, either in the positive direction or in the negative direction. So the maximums of your derivative and the minimums of your derivatives, right? That's where the biggest the slope is and the smallest the slope is. Those are your points of inflection. Lots of ways to justify it. I would recommend you just always do the first one. Right? And if you always do that one, there's no confusion. You're going to get them right. Something has a point of inflection when that same something changes concavity. That will always work. If you want to conceptually kind of understand and tie it to some other things, that's fine. The second derivative of G, which is the first derivative of f, second derivative changes sign. The first derivative changes slope, where that first derivative changes behavior, where that first derivative has an extrema. Those are all equally valid ways to justify. But all of those would get you to that same thing, right? 0 and then 3, the max and the minimums of that first derivative. Those are the locations where the original function would have a point of inflection. So this function defined by integral, it really ties back a lot to the stuff that we've been doing. The new stuff, right? The new things, now that we know integration, the new stuff is the part A, where I can look at the areas bounded by these derivatives, and I could use those areas to find y coordinates on the graph, right? So basically the new stuff is right here, the area bounded by the derivative. Let me zoom it out. The area bounded by the derivative, that's going to give us the change in the y value, so I can find what those y coordinates are. This would be a really, really good thing for you to know, right? Conceptually, this covers a whole lot of questions on that AP exam. I'm going to leave it here for about 10 seconds before I end the video. If you need to pause it to copy it down, you should, right? This, conceptually, is very important. The fun chart in this little diagram, it's really the same stuff. It's just different ways of visually organizing it and presenting it so that hopefully you can understand it. But all this is important. If you are hesitant or if you're iffy on any of it, you should copy this down, and you should every night you should just read it right before you go to bed. That way you dream about calculus, right? This is good stuff right here, right? If you don't know it, copy it down and then just keep practicing. All right, so that'll be the end of this video. We'll pick it up with the next video, and then we'll kind of power through the end of this notes packet. Again, pause the video if you need to. Otherwise, just keep on chugging and watch the next one.